In this video, we will discuss the current in heterojunction. So in a heterojunction, the energy barrier or the potential barrier between the two sides, P and N side, is modified by the band offset. So there is a conduction band offset and the valence band offset as shown here. So the actual barrier height for electron is given by Q sub phi Bn here, which is the total band bending minus this conduction band offset. And the valence band offset also, the delta EV valence band offset also modifies the total band bending and determines this actual energy barrier required for holes to overcome to come to the other side. So this interplay between the total band bending or the built-in potential and the band offset is what actually ultimately determines the current in PN heterojunction. Now there are two types of current that can flow in PN heterojunction depending on the band alignment. You could have the same old diffusion current as was the case for PN homojunction, but we could also have a thermionic emission current, which is the actual current mechanism that we have in the Schottky contact, metal semiconductor Schottky contact. So let's first consider the case where the spike here, the maximum energy point for the conduction band of material 1 is actually located at lower energy than the conduction band of material 2. If that is the case, the energy barrier for electron is determined by the conduction band of material 1 minus the conduction band of material 2. And the potential barrier for energy barrier for holes are the conduction band offset plus the band gap difference. Now, the majority carriers on each side is given by the usual equations, and it is equal to the doping density. And similarly, so for material 1, majority carrier is equal to the doping density, and the minority carrier in material 2 is given by the similar equation. So this is the equation that we derived for non-degenerate semiconductors, and you can set up the same equation for hole concentrations. Now, as you apply voltage, you are changing these potential barriers. So forward bias reduces the potential barrier just as it did for homojunctions. So the minority carrier concentration is given by this diffusion current equation, the same old diffusion current equation. So this gives you exactly the same equation as we did for the homojunction, except that you have to use the intrinsic carrier concentration for material 2 in this case. So if you are going to rewrite this equation in terms of the Ni, intrinsic carrier concentration of material 1, then you have to account for the band gap difference, which introduces this extra term here, exponential delta Eg over kT. So the injected electron current is the same for the homojunction made of the smaller band gap of material 2. However, it is larger than the homojunction made of the larger band gap material 1, because you are going from a larger band gap material to a lower band gap material, and therefore the energy barrier is lowered by the band offset, conduction band offset, delta EC. And this is the equation for a long base diode, and that's why we use this diffusion length here. And for a short base diode, all we have to do is to replace the diffusion length with the length or width of the quasi-neutral region in material 2. You can do the same exercise for hole current being injected from material 2 to material 1 and derive the same equation. And it is noted here that both the electron current and hole current are independent of the conduction band offset or the valence band offset. but only depends on the difference in band gaps. So in other words, it does not matter how the bands are aligned relative to each other. The difference in band gap is the only factor that matters here. If you have a situation where the notch of the maximum energy point for the conduction band of material 1 actually is located at a higher energy than the conduction band of the material 2, then the total energy barrier for electron is determined by the band bending on the material 1. So the energy offset the location of the conduction band of material 2 is irrelevant in this case. Now the current depends only on the energy barrier on the n-type side. So your electron current is proportional to exponential negative q phi bn over kT, and this type of current is called the thermionic emission current. And if I may go back to the previous slide here, what does that mean? That means electron here needs to overcome this barrier defined by the band bending on the n-type side. And how do these electrons do that? Well, some of these electrons have high enough thermal energy to overcome this barrier, and only those electrons will come over. And that's why it's called a thermionic emission current. And this is the same current mechanism that has the that is at work, operative in the metal semiconductor Schottky contact. And so as the forward bias is applied, the voltage is dropped across the entire depletion region, but only a small portion, only a portion of it that is dropped on the N side affects the barrier height on the N side. And those voltage that is dropped on the P side of the depletion region don't affect the current. And so therefore that produces a different voltage dependence than the diffusion current case, in which case the entire applied voltage affects the current. So if you plot the current as a function of voltage in a semi-log plot as shown here, diffusion current and the thermionic emission current has two different slopes arising from this different factor inside your exponential function, and therefore they become dominant at different ranges of your applied forward bias.